Hi everyone, good morning, good evening, good afternoon, depending on where you are. My name is Shima Abadi. I'm a faculty at the University of Washington, and my research area is underwater acoustics, ocean sound. So I study the sound that propagates in the water column technically. In the past couple of years, I was exploring the use of DAS for ocean acoustics, and this presentation is mainly on that topic. Can we use DAS for ocean acoustics? And if we can, what are the limitations? As always, this presentation is not just my work, it's a teamwork. We have a great team of people who are doing research related to DAS, either in geosciences or ocean sciences at the University of Washington. So you see the name of some of them here. And so it's a collaborative work, it's a teamwork. Okay, so let me start with talking a little bit about ocean acoustics, since this topic might be different from other talks in this group. So in ocean acoustics, we care about sound in the water column, and then we keep track of that. We are interested to know where the sound is coming from, which direction. So we want to find a location or direction of arrival. We want to characterize it. So we want to, if we are listening passively, we want to know where the sound is coming from and from which type of sources. Underwater, we know that we have a lot of sources of sound. It can be on the sea surface, like ships are generating sound, wind, rain, waves. These are the type of things that generate noise underwater. In the water column, we have marine mammals, we have snapping shrimps, we have other type of species vocalizing and generating noise. And on the seafloor, we have earthquakes, we have volcanoes also contributing to the ocean noise. So in ocean acoustics, typically when we want to measure data, we deploy hydrophones underwater. Hydrophones are typically like microphones that operate underwater. We can have different configuration of hydrophones. We can have a towed hydrophone towing behind either a vessel or a glider. We can have hydrophones on a mooring at different depth. We can have hydrophones on the seafloor, like bottom-mounted hydrophones. But there are some challenges typically with this type of experiments. Well, the deployment is hard, recovery is hard, but the main challenges are the spatial resolution. The spatial resolution is limited. So we have single points, so it's single point measurement technically. Although sound can travel long distances, so what we receive can be from very long distances. But what we measure is the sound received at that particular point. With single hydrophone, it's so challenging to do localization, so we typically need an array of hydrophones. So we deploy a couple of them in different configuration to find the location of the source, either in 2D or 3D. Real-time monitoring can be challenging too, unless we have cabled hydrophone. And as we go under the sea surface, we lose connection, so we have no connection to the satellite unless the hydrophone is cabled. So having real-time monitoring can be challenging with hydrophones. So these are some challenges that we think DAS can resolve. And by using DAS, and I'm sure you all know that we are using fiber optic cables, and in my application, submarine fiber optic cables that are on the seafloor. It can be buried, it can be on the seafloor. And we can technically measure sound every few meters, and it can go up to 100 kilometers. So we are increasing the spatial resolution suddenly, compared to the hydrophone. And but there are still some challenges that if we want to use DAS in ocean acoustics, we need to study and understand. One of them is low signal to noise ratio. So DAS channels have low signal to noise ratio compared to hydrophones. But we hope that we can increase the gain by having thousands of receivers and doing some sort of signal processing algorithms to increase signal to noise ratio. At the end of this presentation, I will show you an example of that. The other thing is channel response. So we are using hydrophones for many, many years. We know how to measure the instrument response. We know how to incorporate that. But with DAS, this is something new. And we need to first find out what is the channel response in terms of frequency and other recording settings. and then how to incorporate that to the data, to the raw data that we collect. And the last challenge is the main one. The main one is the large volume of data compared to the hydrophone. So we are not used to collecting terabytes of data, and our algorithms are not optimized for that. So we are still learning how to process the data. Okay, so I'm sure you all know how DAS works, but just to be on the same page, we send a laser pulse in the fiber optic cables. We look at the backscatter signal from inhomogeneities in the cable. And then by looking at the phase shift, that phase shift is related to strain along the cable. And we can convert the raw data, which is phase shift, to strain or a strain rate. And then that is an indication if there is a sound source somewhere in the, along the cable, we can have a measurement of that. DAS has been has many applications in seismology, earth sciences, ocean sciences for a couple of years now. So I'm sure you can find a lot of other papers related to those topics. But in ocean acoustics, there are just a few papers. And in addition to what I have in this slide, there are a couple of more that were published recently. So it's just a new technology, new sensing technology in ocean acoustics, and people are still trying to figure out what they can do with that. So in this presentation, I'm going to talk about two data sets. I'm going to use the first data set that I'm going to use is OOI DAS. Some of you might be familiar with that. And then the second data set is DASCAL data set, which was collected from Puget Sound. So I'm going to talk about each one of them and how I use that data separately. So first, OOI DAS experiment. So Ocean Observatories Initiative is an NSF-funded project that has more than 800 instruments in the ocean collecting data in almost 24/7. And one of the networks, the Regional Cable Array, which is off the coast of Washington, was down for maintenance in November 2021. And we decided to take advantage of that and implement DAS, and we collected DAS data on two of the cables, North Cable and South Cable, for 4 days. We had different measurement settings, different engagement, different sampling rates. And the data was available after spring of 2022 after Navy screening. So a little bit more about the cables. We had two cables, not completely parallel, which is good for localization. The North Cable was 65 kilometer, so we can record up to the location of the first repeater, which for North Cable was 65 kilometer, and for the South Cable was 95 kilometer. And both cable went down pretty much in the deeper part of the ocean. North Cable was the deepest part was about 600 meter depth, and South Cable was more than 1500 meter depth. We recorded thousands of fin-well calls in that data set. So what I'm showing here, what you see on the top panel is the bathymetry. X-axis is distance from the shore. So shore is on the right-hand side. And then I show bathymetry, so ocean depth on y-axis. And then the second panel, the bottom panel, shows time on y-axis with the same x-axis. So this is the TX plot of 6 individual whale calls. So all these V-shapes that you see in the data, these are individual calls. The tip of the V-shape shows where the animal was closest to the cable. So there was probably an animal closest to the cable at about 30 kilometers from the shore, and there was another one at about 50 kilometers from the shore. And then so the channels here received the signal first, the channel further away received the signal later, and that's why you see this pattern of straight line. And the slope of this line is about 1500 meters per second, which is equal to the average speed of sound underwater. So these are just 3, so you can see 3 vocalizations here and then 3 here. And this is the typical fin-well vocalization that we expect to see in this region at this time of the year. And I'm showing the spectrogram of this is the average of, I believe, 10 receivers. So very tiny section of the cables here over time. So what you are seeing is the fin-wheel vocalization around 20 hertz. This is the typical fin-wheel calls. It's a downsweep, very short period, 1 millisecond, about 1 millisecond, and the center frequency is around 20 hertz. So we see 3 of them here, and if you look at another spectrogram here, you see another 3. So what we saw in the OOI data that we can record fin-wheel vocalization. Not only we can record it, but look at the extension that we can record. So this shows almost 60 kilometers of the cable. And for a single vocalization, we can see the call pretty much on the whole cable on all the channels, which is pretty amazing. So we have 60 kilometers of the data collecting the same vocalization from the same animal, so we can increase the signal to noise ratio. We can do localization. In this paper, William Wilcock has done localization on fin-wheel vocalizations, and so it's a very rich data set in terms of marine mammals. And we also recorded a lot of blue whale calls. So what I'm showing here, again, this is the TX plot. What you see here is a blue whale call. It's a B call. And then all these lines are fin-wheel calls that we're vocalizing at the same time. And again, if you look at the spectrogram, you see the B call, which is about 20-30 second call, and at different harmonics. So we were able to show that DAS is able to collect low frequency species, vocalization of low frequency species, between 10 to 25, 30 hertz. And that's pretty amazing. We also recorded a lot of shipping noise. So what I'm showing here is the path of a bulk carrier that is going south to north, passing both cables. And we have this data from AIS, so we know exactly where the ship is at any time. And looked at the data on the north cable, we see the ship path right here, and on the south cable we can see that clearly. You can also see in the north cable, you can also see some fin-wheel vocalization in the background. In order to see the data, we know that DAS is contaminated with a lot of noises, especially surface wave gravity, so we need to filter the data, the typical bandpass filtering, and we also did FK filtering to remove noise from other directions. And then if you look at the spectrogram of that noise, we see a broadband signal. That's a typical signal we expect to see for shipping sound. And you see different harmonics here. Zoom in into the TX plot. This is the closest point, and we all know that DAS is blind when to the broadside. So at the closest point, when the ship is exactly on top of the cable, the angle is 90 degrees and we don't hear anything. But when we go further away in other channels, we start recording. So we start recording here and here. I will talk about this detection range in just a few seconds. So for the north cable, the path was almost perpendicular to the cable, so you can see the straight line. But on the south cable, the path was with an angle, and you can clearly see that angle here. So it's very easy to track shipping noise with DAS. And if you're really zooming into time, and this is just 1 second of the data, you can see the interference. This is the interference between different paths, the surface reflection, bottom reflections, and direct path that we expect to see. And then this shape shows the interference at different time and different location. And you can also look at it as frequency if you want to. So talking about detection range, what I'm showing here is the energy in the band that we expect to see shipping noise for different channels. So this shows channel number versus the spectral level. And then this region is the blind spot. It's about 600 meter or 3,000 channels that we can't hear shipping noise. But right after that, energy goes up and then gradually decreases. This blind spot is because of this cosine square in the equation of that we have that technically the equation shows the relationship between a strain and particle velocity, and then we have a cosine square of bearing, and when theta is 90 degrees we get 0 measurement, so that matches with what, based on the equation, with what we expect to see. But then if you look at the detection, the energy goes up and gradually goes down until we get back to the ambient noise. And this range is about 6 kilometer or 3,000 channels. It's different from what we had in fin whale vocalization. In fin whales, we had over 60 kilometer. But for shipping, it's much smaller than. This is what I'm going to talk about in a second. But still, we have 3,000 channels, and we can do a lot of signal processing algorithm to localize that. In the paper that we published with William Wilcock and Brad Lipovsky, I showed how to do beamforming for shipping noise, and the beamforming matched very well with the AIS location. But in order to talk about the detection range, first we need to understand the channel response, or the impact of moving the gauge length basically in our measurement. So what we are measuring, because laser pulse has a finite width, is not a single point measurement. It's the average over a specific length of the cable, which we call gauge length. It's the setting that we can change when we collect the data, but it can go very low to just a few meters, or sometimes below that. But typically in the OI data, it was between 30 to 50 meter. So what we measure is the average of 30 or 50 meter. And if you think about it, so what in this space, we are measuring different data points, and we are averaging technically in a space by having this gauge length effect. So that is like having a moving average in our data. And if you look at the frequency response of a moving average, this is the frequency response of that, which is a function of GL, gauge length, and also frequency, and also bearing, theta. So what I'm showing here on the right-hand side is a moving average response normalized as a function of frequency for single gauge length, but at different bearing. So when the bearing changes, you see that this null, the frequency, the zero response, the location of that will change. And that means at 0 degree, if you do the math, this location is about 30 hertz, which is 1500 meter divided by 50. So 50 was the gauge length, 1500 meter is the speed of sound. And then we get multiples of that. So it repeats, it goes up to higher frequencies. So if you have a signal below 30 hertz, we can get a good response, or we can measure that really nice. But if you have a signal at higher frequencies, the amplitude will suppress. And at some frequencies, we don't hear them because of the null location. So that's the main reason that fin whale vocalizations, we didn't see any impact of gauge length on fin whale vocalization, because they are mainly in this main lobe, they're 20 hertz, so below 30 hertz. But for shipping sound, because it's broadband, and actually the main energy, if you look at some data points, it's between 30 and 70 hertz. So it's in the higher frequency region, which the amplitude is suppressed because of the effect of gauge length. And that's why the detection range decreases. I just want to say it's not that easy. It's just a nice explanation, but when we want to do the math, it's not that easy, because bearing, we don't know exactly about the bearing, because we have multipath, especially in shallow water. So we have direct path, surface reflection, bottom reflection. So we have different bearings, and that will kind of like make the whole analysis a little bit more complicated. But that's the overall what happens. So if we look at one channel, single channel energy or spectrum, in this case, I'm just showing this channel for channel 42,710, and the black line is the spectral level as a function of frequency. This is for a shipping noise, so it's a broadband sound. And the blue is showing the gauge length response. I calculated gauge length because I know the gauge length, and I know the bearing because based from the AIS data, I know the location of the ship, so I can calculate the bearing. So what it shows that at this channel, we have a good response, so all the frequencies are present, and that's why the spectral level is so high. But if we go down here at channel 42,000, for example, the gauge and response is that the null locations are getting closer to 30 hertz and higher frequencies are suppressed. So that's why the spectral level has decreased, and that limits the detection range of the shipping noise. But again, going back and compare the detection range of shipping noise with fin wheels, we don't have this issue with fin wheels because even at the 0-degree bearing, when the null is at 30 hertz, we still have a good response at 20 hertz. So we can see the fin wheel vocalization in longer distances until the spreading loss decreases the amplitude and it's lost in the ambient noise technically. Okay, so that was the impact of bearing on gauge length, but I said the gauge length is a setting that we can change when we collect the data, so we can go lower or higher. And this is just a simulation showing the gauge length response for different gauge length, 10 meter, 30 meter, and 50 meter. So what it shows that if we go to lower gauge length, 10 meter, for example, we are pushing the location of null to higher frequencies. And then we have a bigger lobe here, so with higher amplitude. So if we have a frequency, like say we are interested to record 200 hertz, for example, we have a chance to record 200 hertz here at 10 meter, but very low chance of recording 200 hertz at 50 meter or 30 meter gauge length. So this is just a simulation showing what's the impact of gauge length. And in ocean acoustics, a lot of sources are at higher frequencies. A lot of species vocalize in higher frequencies. We have different type of noises that can go up to really, really high frequencies. So we want to know, we want to check this hypothesis technically. If we go to lower gauge length, can we record higher frequencies? So to understand that, we conducted another test, DASCAL 22 experiment, which we use about 4-kilometer submarine cable connecting 2 islands in Puget Sound. And we collected data. We also had hydrophones for comparison. And we used a 3-meter gauge length. So we went really low. And then during that experiment, we had a sound source that we had off the boat from one side of the boat, and we were drifting. So this sound source was producing sound, and we were able to record it by the DAS cable on the seafloor, and also a hydrophone, actually 3 hydrophones on a mooring with this setup that you can see. So the depth can go as deep as about 90 meter, and it's kind of like flat everywhere, and we have a very steep slope at the beginning and at the end of the cable. So when we get closer to the island, we have a slope. The sound source that we use, it's called bubble pulsar. There are 2 plates that they get close together, kind of like clap like this, and generate noise every 5 seconds, if I remember correctly. And then we had it off the one side of the boat right here. We deployed at different depth, and we were kind of like shooting for a couple of hours, and the boat was off, the engine was off, so we were just drifting. And we also had a hydrophone close to the source, so we could measure the source signal. We had different characteristics at end fire versus broadside. So we had some big energy between 300 to 500 hertz at end fire direction. And this is what we will see in both DAS and hydrophone data in just a second. So on the DAS side, I'm just showing just a couple of recordings showing that we were able to record this high frequency noise on a couple of channels when the source was at different depths. So in all of them, we were able to record. And then this is a zoom out version showing channel number versus time, and what all these pulses basically that you see is the signal, the source signal that we were broadcasting. And here we show the location of the channels that I'm showing on the right hand side. Blue is the location of the sound source, and red is the location of the hydrophone data. So this gap, this little gap that you see here and here, is when we were changing the depth of the source. So we were not broadcasting in that short period of time, but you can see that we were collecting those signals pretty much in a lot of channels, but most of those channels were on the slope. I am showing the common receiver gather here, so shot number, different shot numbers stacked versus time. This the two left panels, or the left or the middle panels, are DAS recordings from two different channels, and the right recording, the right plot, shows what we recorded by the hydrophone. So what you are seeing here, you see clearly two arrivals right here, and they are merging together, when the shot number increases, and that's because we were drifting, so the source location was changed. And then here we show a simple simulation to show the path. So one of them is the direct path, the other one is the ghost signal, the surface reflection. Same here, but we're not recording at this depth. Let me explain. This gap here, right here and here, is when we change the depth of the receiver. So we had 10 meter, 5 meter, and 1 meter. At 10 meter in this channel, we were not recording the signal, but at 5 meter and 1 meter, we were recording. And for the hydrophone, the path is more complicated because it's the channels of the DAS that I'm showing is on the slope, but the hydrophone was in the middle of the distance between the islands. So they're not at the same location. The arrivals are different, and the simulation shows which arrival we are seeing in the data. So looking at the spectrogram, so what I'm showing here, the top one is the hydrophone. We see 6 shots, technically, 6. And the DAS is the bottom panel, and you see frequency versus time. So on the hydrophone, it's a broadband source signal, we can measure that. And on the DAS, you can see that we have a little bit of energy below 200 hertz, and then some main energy between 200 and 500 hertz. So we can clearly see the shots here. This is single channel DAS. And then just explaining the differences between the spectrogram of hydrophone and the spectrogram of DAS, I'm showing the channel, the frequency response or gauge length response at 6 meter gauge length, and it shows that we have a null at about 200, a little bit more than 200 meter, and that's exactly the location that we don't see any energy here, and we have and we have a good energy above that, and that's because if you remember the spectrum of the source, when I showed, we had a good energy between 300 and 500, and that's the energy that we are recording. So technically this experiment shows that we can record higher frequencies if we go to lower gauge length. And the other thing is comparing, if you go back to the spectrogram, you can clearly see the difference between signal to noise ratio between hydrophone and DAS. But we decided to stack them, so we have a lot of shots. If you stack different shots to get we get a better signal to noise ratio. So what I'm showing here is signal to noise ratio versus frequency. Black line shows signal to noise ratio for hydrophone. It's pretty high for all frequencies. This line with diamond is single channel DAS, and the line in between is when we stack 15 shots together. So we are increasing signal to noise ratio. If we have more shots, obviously we can get a better answer. This is a stacking in time, basically, in shot number. We can also stack in channel numbers. We have multiple channels. So again, this gray line is single channel DAS signal to noise ratio. Black line is hydrophone signal to noise ratio. Blue is a stacking in shot or stacking in time, technically. And red is a stacking in a space. So what is showing is that stacking in a space or stacking in channel basically is improving pretty much all the frequencies here. Even at higher frequencies, we're getting more energy, a better quality signal. Okay, so just to wrap up, so we have time for discussion, what I wanted to show you is that submarine DAS can be used for ocean acoustics, but there are still so many things we need to understand. With optimal settings, we were able to record signals even at higher frequencies, a couple of hundred hertz. And then we are trying to see if we can increase that. So we are trying to see if we can go to higher than that. There is literature showing that DAS can record up to 2500 hertz, but can we go higher than that if we go to gauge length lower than 1 meter? And you know that signal to noise ratio will be lower as we go to lower gauge length. But then a combination of small gauge length and stacking, can it improve the signal to noise ratio? And then the detection range on DAS decreases with frequency, because if we go to higher frequencies, the gauge length response will be, the amplitude will be lower. And then the other thing I showed is that with the stacking, we can improve the signal to noise ratio. And that's the beauty of DAS. So I'm going to stop, see if there's any question. Thank you so much.
That was so interesting. I have been thinking about acoustics recently, and I'm not an acoustics person, and this is an awesome talk. So thank you so much for that. I have some questions, but maybe I'll just open it up to anyone else first. Does anybody have any questions?
Why you stop sharing? Let me go back to my presentation.
I think you can go ahead, Luis.
Yes, thank you. It's a pity I got a little bit late in the presentation, but still I have one question regarding one of your last slides. Mm-hmm. So you show that in the DAS you have a notch at about 200 hertz, but on the signal to noise ratio there is not any information on that notch. So I really didn't understand how did you measure your signal to noise ratio from the recordings that you showed earlier.
So this is so I should mention that each single point, the signal to noise ratio is the average over some band. So that's why it's not showing the notch at those frequencies. It's the average of some frequencies.
Yes, but if you don't have any signal at 200 hertz, then the average should be identical to the noise window. So it should be, signal to noise should be 1 if you don't have any signal at 200 hertz.
Correct, but if you so it depends on the stacking, because that's actually more complicated. So this is single channel DAS that I'm showing and shows the notch, but if you go to another receiver next to that, the bearing will change. So you may or may not see the notch exactly at the same location. And when we do averaging over multiple shots or multiple channels and multiple frequencies, that effect is gone, if it makes sense, because this notch location is a function of theta 2, bearing 2. And when we go to different channels, that bearing changes.
Okay.
Let me show you the one that I had with bearing, maybe not here, this one. So this one shows when the bearing changes, this location of the notch will change.
Yes, but what I want is, if I want to locate the source, it's a single pulse that I want to locate. It's not an average of hundreds or tens of pulses or hundreds of pulses. So that measure of signal to noise ratio doesn't seem to me useful for the evaluation of the location of sound sources using DAIs. That's my opinion. I was misled by that. I was misled completely by that plot.
I'm not quite understand your question. Could you explain more?
No, it was not a question. It was just a comment that I was misled by, after seeing the spectrograms. and then not seeing the notch in the signal to noise ratio, I was confused. That's my comment. So like that.
Any other questions? No one else has questions. I was also curious about the detection range and the bearing, the 2 slides previous. So that blind spot, and I might just be not imagining the geometry correctly, that blind spot will vary depending on the track of the vessel over the cable, or
Yes.
whatever the source.
Yeah, it's when it happens when the ship is exactly on top of the cable. So we have exactly 90-degree bearing. So
Okay.
maybe you can see it better here. So that the track is perpendicular to the cable, so it's
Mhm.
moving, right? But it's the bearing is always 90-degree, so we don't see any signal here.
Yeah, okay. That makes sense. I'm curious if you've seen any, or if you've looked at the differences between the cable burial for these 2 experiments and how that's impacting your signals.
That's a good question, and no, I didn't look at the differences between experiments, but for the experiment in the Puget Sound area, the interesting thing is, maybe I can go back to this plot. So we only saw the high frequency signal on channels on the slope, not the other channels. And we believe that it's because this part, the sediment, it's too loose, the cable is not burial, there's not enough sediment on top of the cable. So this burial effect might have it might cause some issues at higher frequencies, which we still don't know because we don't know which part of the cable was buried or not. This is just a guess. So it might be true, it might be that high frequencies can only be recorded when we have cable on the seafloor, so they have a good coupling with the water column.
Mm.
It impacts higher frequencies because higher frequencies dissipate so fast when we have sediment. But we still don't know.
Yeah. So theoretically, there'd be some balance between the cable being buried and well coupled, but
Yes.
not buried so deeply that the sound attenuates before it impacts the cable.
Exactly.
Interesting. Yeah. Okay. Looks like there's a question in the chat from Chris Minto, who asks, did you use the geometry of the null to locate the depth in the water column of the whales?
We did not use that. Before localization, we used the TDOA algorithm, time difference of arrival at different channels. And it actually, we don't have any other information to confirm the location that we had is correct for the OIDAS data, unfortunately. So we had no visual observation or no tagging to confirm that.
Hmm.
Yeah, I just add to that. What I was meaning was more, I mean, it might not even be useful, but by the way, this was a great talk. I absolutely loved it. It's great to see people doing this work. But once you know from the surface craft the width of that null, you've essentially calibrated the beam pattern of the cable because you know the height of the water above it, and that gives you then a simple Pythagoras arrangement. So if you can, you know, as the craft get lower and lower in the water, as in the whales themselves, the null will shrink because the angle stays the same. And so you can then, you've got a mechanism to know how deep in the water are the whales. That's what I was getting at rather than to geolocate them.
Oh, I see. That's actually a great idea. No, we didn't do that. It's actually a great idea. But I don't know, I'm not a marine biologist. I don't know if how much variation in depth animals have when they vocalize. And we never explored that. So, but that's a great idea.
I'm curious if you have what your next big goal is for these two data sets.
So for OIDAS, we are exploring the fin whale and blue whale vocalization in more details. So we are trying to have more sophisticated algorithm for localization and understanding, during this 4 days, it's not a huge data, but over 4 days, where they are most of the time when vocalizing, and if we can see any pattern in the vocalization and location also. And also we are we have other data sets right now and a couple of projects in future to explore higher frequency capability of DAS. So that's what we have in future.
Oh, and I see Ethan has a question.
I do. I'm curious about the multipath that you described. I know there's I don't think you showed a slide, but it's easy to kind of draw a fancy ray diagram and show in shallow water how there's all these different reflections and how they must take over at different places. And you can kind of see in the raw whale data where these gaps in sensitivity from the kind of vanishing or the critical angle of the different reflections are. I'm curious if there's enough redundancy in coverage of the water column from these paths, and if you can actually see them kind of separately, that you could use this as a kind of tomography tool. Is there any way to really isolate, the direct path from the first multipath, from the second multipath, so that you could measure, for example, the position of the source relative to the changing wave speed of the water column over tidal cycles or seasonal cycles? Are whales useful for that, or is it just too complicated?
That's actually a great point, Ethan. This is what I'm thinking these days. So for ship, it's probably more complicated because it's a broadband source. But I should say that with simulation, we saw the same pattern. So exactly like what I had here. Where was the ship notes? Like this pattern that you see here. So in the simulation, we can see that if we run the simulation for different locations and distances. But it's more complicated to separate that because it's broadband. For fin whales, we might be able at long distances to see the separation. For shots that we had in the DASCAL experiment, we can clearly see different arrivals. So we have direct arrival and surface reflection, so we can separate that. And then we can do what you would describe exactly. So this is something I'm thinking and working on these days.
Do you think that there's enough, that the uncertainty in the location would ever be small enough for this to actually work? Because, the sound speed changes are so small, right? They're a fraction of, 1% typically over shorter time scales. And so presumably the actual precision of the measurement would need to be really precise. We have a lot of channels, and so that should at least help theoretically in a kind of square root n sense. But do you have a sense of how accurate the locations are or would need to be?
I don't know exactly. Most of these experiments, we have AIS, and the AIS has some error, obviously, and some time lag. So that's an issue. But I don't know. I mean, for understanding the impact of like this speed of sound profile or some other variation that you mentioned, we need longer data, longer period data, which we don't have here. This was just a couple of hours, and OIDAS was just 4 days. It might be easier to see in other data sets that if we record for a longer period of time. But what we can do with this is seeing the impact of the bearing on gauge length response exactly, because these two paths have different bearings. So if we look at the spectrum, we should see different notches. And is that true or not? Is that what we think in theory that happens, is that exactly what happens in measurements?
One thing that could be fun to try, I haven't done this at all, but would be to do interferometry on the whale calls, not on the noise. There's a whole literature in the kind of oil exploration industry that kind of precedes ambient noise interferometry. There's a bunch of papers by Schuster from like 2000, 2004, where they use localized sources like drilling noise downhole. It's basically a point source of noise. And the advantage of doing interferometry is that you're able to get out the relative travel times for this repeating source without having to, and potentially moving source without having to account for the absolute geometry. You can just look at relative rate path geometry using the interferometric travel times. So that could be a fun thing to try to see if that yields anything useful in terms of separating out these different paths. Though it's super interesting. Thanks for your talk. It was great.
No, that's a great idea, Ethan. I have a PhD student who worked on the interferometry with DAS, and we saw the challenge of multipath and the effect of gauge length, because depends on the pair of the channel that you pick, you may not be able to resolve the arrival angle that you expect you see for that pair, because of either the DAS is blind to broadside or it's the gauge length effect. So it's actually a little bit more challenging, but that's a very interesting area to explore more.
Awesome. Shima, thank you for a wonderful talk. And I think I will be getting in touch in the future to talk to you more about acoustics on DAS. I have some detailed questions that the rest of the group doesn't need to hear my naivety about acoustics. But this was a wonderful talk. I'll give one last opportunity to ask questions, and if not, I'm sure that Shima would be available via email to talk more. And this will be posted on the same YouTube channel as the other DAS RCN talks.
Thank you so much for inviting me.
Yeah, this was wonderful. Thank you so much for giving a talk. It was great.